Well, thank you, Laura, for inviting me back to give a talk. I enjoyed giving a talk the last time round, and I think there's an awful lot that's happened in the last 3 months, 4 months from when I last gave a talk. So hopefully this is a bit of a chat to catch up with what's going on with COVID-19 and vaccination. I'm Julian Mitchell. By training, I'm a geneticist. I should point out now that I'm not a medic. I'm not a medical person. I'm not a clinical microbiologist. My interests are solely in the genetics of organisms. I did my PhD in virology, and hence I have a specific interest in the genetics of viruses. What I want to do and talk to you about today is really to cover some basic ground on what is vaccination and what's actually in a vaccine. And then looking at how the different vaccines are made, particularly reference to the vaccines for SARS-CoV-2, which is the causative agent of COVID-19. And then look to see specifically what's in these vaccines, and then to talk a little bit about the worries about vaccines and vaccination, and with particular reference to the COVID-19 vaccines. There's been a lot in the papers and in the news recently about whether certain vaccines are better than others and whether some vaccines cause problems. So I'll have a look at the information that's surrounding that. And then I want to finish off by encouraging everyone to get vaccinated and looking at the reasons why you should get vaccinated. Okay, so to start off quickly, what is vaccination? What do we mean when we say vaccination? Well, the modern version of what is vaccination is that it's a training scheme to actually help your immunity system recognize specific pathogens so that it can destroy them. The vaccination does that by administering a vaccine, usually by injection, but it can be done by other means, into the main muscle area where it gets picked up in the blood systems. Now, where all the protection level comes in is at the blood level, and in particular, it's what happens to the white blood cells. Now, if we look at white blood cells, we find that there's a myriad of different types of white blood cells, and broadly, we can group those into innate cells. These are cells that are present in the body all the time, doing specific jobs to destroy foreign particles. Okay, so that we have the innate cells and we have what's known as the lymphocytes. And the lymphocytes, there are many types of lymphocytes. The ones that we're particularly interested in with the response to a vaccination program are the B cells and the T cells and what's known as the memory cells. Now, when a pathogen enters the blood system, it gets tracked down by one of these innate cells. These are usually referred to as phagocytes. And they chase the invading pathogen, whether it be a bacteria or a parasite or a virus, and it will digest those pathogens down. Now, as it digests and breaks down the pathogen, it actually exposes parts of the pathogen to the outside. Okay. Now, these parts that are exposed are often referred to as the antigens. Okay. Now, the reason why it's exposing these fragments or antigens, if you like, to the outside, is so that it can communicate with the lymphocytes. And it communicates with the lymphocytes via what's known as a T helper cell. So this is one of these T cells, but the T cells that interacts with these other cells that are digested down, it then copies the antigen and takes it to the other cells, and particularly into the B cells, which then mimic the antigen and make a copy of a protein that can bind to it. And it's these proteins that are then exported, and these, of course, are the antibodies. Now, because it's proteinaceous in nature, this means that we can follow, during infections, the production of antibodies. And there's not one antibody that's produced in this means. There are many antibodies that are produced in this way. Some are different types of antibodies that are produced, and in different parts of the body, different types of antibodies are produced in different parts of the bodies. So in actual fact, what's happening here is a learning process, because if the antibody can bind to the antigen, it can then bind to the pathogenic cell or virus particle. Now, sometimes with viruses, that's all you need, because if the antibody can block all the receptor sites on the virus, then the virus can't gain entry into the cell and cause an infection. The other side of the story is to do with what's known as T cells. And the T helper cells can also form what's known as T killer cells. And these T killer cells are cells that recognize things that have been tagged with the antibody. They chase them down, and they actually then destroy the cell or the particle that's been tagged by the antibody. Now, where we're coming in with vaccination, of course, is what we're doing. We're using what's known as a vaccine. Now, a vaccine can either be a dead or inactive pathogenic cell. It can be an inactive or dead virus, or it can be a protein from the pathogen, or indeed it can be a toxin from the pathogen. It doesn't necessarily have to be a full pathogen or inactivated pathogen in some ways. For instance, just to give you an example of that, the diphtheria vaccine that was produced in the 30s and 40s wasn't actually anything to do with the bacteria that produces the diphtheria toxin. It was actually a form of the toxin itself that actually initiated an immunological response. Okay, so by mimicking and producing antigens that can interact into the blood system, be picked up by the T helper cells, in that way we can actually produce antibodies to the specific antigens that we put into the blood system. Okay, and in this way we're actually producing a training. Now, there are other components around that are also interesting that you're going to hear about later on as the talk goes on. And these are called adjuvants. Now, adjuvants are molecules that actually stimulate the immunity system. Okay, so they can actually stimulate the production of your innate cells. Now, the trouble with having the B cells and T cells that are produced in response to an antigen that might have been produced either through the innate cells or through the vaccine is that they are short-lived. They're not necessarily around all the time. And they actually die off in the system, except for a small number of them. And these are often referred to as the memory cells. And the memory cells, of course, are longer lasting in the body. And they come into action when the body encounters the same pathogen a second time. Because although the B cells and T cells that originally were using to produce the antibodies and the killer T cells, and these have died down, but the memory cells remember those, and they stimulate the B and T cells to produce antibodies and killer T cells to actually neutralize and destroy the pathogen. Now, once that happens, of course, you have a boosted level of the antibodies and T cells are within your blood system. You then have an individual protection. Okay, and so this is the start of, if you like, getting protection against a specific pathogen. Now, just to show you that I'm not actually making this up, we've got a little video here, which I shall play, which is one of these innate cells. And what this innate cell is doing is actually chasing a bacterium. You can see the bacterium floating around. This is about times 1,000 magnification. Okay, And you can see that it's actually not giving up. It's actually got the bit between its teeth, and it's going after this bacterial cell like nobody's. There it's got it, and it's ingested it. Okay, so this is actually filmed, and this is actually from YouTube, so you can actually have a look at that and download it yourself if you want to. Now, vaccines are usually delivered by injection, usually injection into the main muscle block. Okay, but they can be given orally. Certainly an example of that is the polio vaccine. I had the polio vaccine in the 16, which was a drop on a bit of sugar, and was taken that way. Or it can be delivered by inhalation via an inhaler. And it is said at the moment that some vaccines for COVID-19, for the SARS-CoV-2 virus, some of those are being developed for an inhaler, which would be good. Often a second injection or booster is often needed, and that's to stimulate the memory cells to produce more of the B cells that produce the antibodies, and the T cells to produce the T killer cells. Okay, now once you've got individual protection, really the great thing about vaccination is that you can gain protection for the population. Okay, now this is important because not everyone can get vaccinated. There are some people within the population that really, if you gave them a vaccine, they would be very ill. And so you really want to avoid giving those. So roughly you're looking at perhaps about 10 to 15% of the population that even if they wanted to, they shouldn't have a vaccine. So having a population protection is of interest. Now, you get a population protection when individuals in the population have individual protection. Okay, and when that reaches a certain level, then the virus cannot be transmitted so easily. So that although it might be present in the population, there's a significant number of people that are resistant to the pathogen, so that it isn't replicated and passed on. Okay, and in that way, the people that actually can't be vaccinated gain a protection. Now, this, of course, you might have heard of this in the press and on the television, and people have referred to that as herd immunity. So how many people do we need to vaccinate before we reach herd immunity? Well, a very simple way of actually working this out is to use this type of formula here. Okay, so this is one way of working it out. There are other ways that are used in the models, but here this is a very simple one. So here we need to know two values to work out how many people need to be vaccinated to gain herd immunity or population protection. The first value that we need to know is the R0 value. Okay, now the R0 value is basically a ratio, and that tells us how infective the particular virus actually is. So if we have an R value of 1, what that means is that one infected person infects one non-infected person. Okay, if we have an R0 value of 10, that means that one infected person infects 10 people. Okay, so obviously the higher the R value, the greater the infectivity of the virus. Just out of interest, the basic R value of SARS-CoV-2 is around about 3. Okay, that's without doing any social distancing or trying to stop the virus from replicating. That's what it would naturally be. The other value that you need is the efficacy value, E. Okay, now what is efficacy? Because that's something that's been mentioned quite a lot in the papers and in the newspaper. The efficacy value is literally the potential of the vaccine to actually stop an infection. The values for this are actually calculated from the clinical trials that are used. Before a vaccine can actually be used on a population, it has to go through a series of clinical trials. These clinical trials are devised to measure different things, health and safety from one aspect, whether there's any adverse effects from another, whether it actually does what it's supposed to do, which is stop infections. Okay, so the higher the efficacy value, the better. Okay, so let's work out if we have an R0 value of 3 and an efficacy of 90%, which in this instance, in this calculation, I'll call 0.9. So if we put that into that little calculation, we can work out that we will get herd immunity when about 74% of the population are vaccinated. Okay. Obviously, if these values change, of course, the number of the proportion of people that need to be vaccinated increases. So let's just say that our R value, our R0 value, goes up to 5, which is actually believed to be the R value of the UK U variant. Okay, so if that goes up to 5, and we put in, and we keep the efficacy level of the vaccine at 0.9 or 90%, then the value, the number of people that need to get vaccinated moves up to 88%. So you can see that by looking at these different values, we can work out exactly how many people we need to be vaccinated. By looking at that account, because the government tells us that in the UK at the moment, we're about, we've delivered about the vaccine to about 40%. Those that have been fully vaccinated, either, which means that they've had both injections, is somewhere around the level of about 4%. So we're a long way off from actually getting herd immunity on that level. What the level of natural immunity within the population is, that's a different question, and that these calculations don't take that into account. Okay, so those are the sorts of things that are to do with vaccination. So what is actually in a vaccine? Well, 99.9% of it is actually water. That's what mainly is in a vaccine. But there are some other aspects that we need to be concerned with about what is actually in a vaccine. The first one of these is the active ingredients, and we've talked a little bit about this. This is a small amount of a harmless form of the pathogen, whether it be a bacteria, virus, parasite, or toxin, that is to be used as the antigen to produce the an immunized agent. Okay, so that one I think is pretty obvious what's in there. Also, remember I mentioned earlier on about adjuvants. Well, most vaccines have adjuvants in them to actually stimulate the immunity system. Okay, so these are substances that are known to actually stimulate either the innate cells of the immunity system or the T cells, so that they're being produced in abundance. Within a vaccine as well, you will find residual traces of compounds that have been used as part of the production of the vaccine. Okay, for instance, a residual trace is sometimes if you're using a vaccine that contains an inactivated virus, then one way of doing that is treating it with formaldehyde. So the vaccine might have very small amounts of that present there. But when I say small parts, these are parts per million. Okay, so they really are quite small. The other main part of what's in a vaccine are what's known as the preservatives and stabilizers. And these are components that are added to the vaccine to either stabilize the protein or the inactivated virus or the attenuated virus in some way, and perhaps to prevent contamination of it. Okay. So there are a number of things to watch out for when we look to see what is actually being injected into us. Okay, so let's move on now to the vaccines and the developments. And there are about 5 different platforms for producing vaccines. Now, when I showed this slide at Christmas in December, of course, there were only 3 vaccines that we could talk about then. Those were the nucleotide-based vaccines, which were produced by Pfizer and Moderna, and of course the viral vector-based vaccines, which was produced by Astrazeneca. And I think at that time I talked a little bit about how those are done. So I'm not going to talk too much about those today because we've already covered those in the previous talk. But I will mention something about the newer vaccines that are coming on the stage. But before I do that, I will say 1 or 2 things, particularly about the Pfizer and Moderna vaccine and the viral vector vectors vaccines like AstraZeneca. One of the things that people have criticized the whole rollout of the vaccines for in the last year or so is the speed with which it's been done. People have said, oh, it's far too quick to be done safely and that we can't do that. Well, it should take at least a year to plus up to 10 years to get a vaccine that works. Well, I think that's not necessarily the case these days. And the big example, and the one that I'm really excited about, is the nucleotide-based vaccines that have been produced by Pfizer and Moderna. Basically, what these vaccines are messenger RNAs that code for the spike protein. Okay, so this is a diagram of SARS-CoV-2, and here we have the spike protein. Spike protein is important because that is the protein that interacts with the receptor that allows the virus entry into the cell. If you actually design antibodies for that, that can bind to that, then you're potentially blocking the entry of the virus into the cell. Now, the way that the Pfizer and Moderna vaccines work is that the messenger RNA for the spike protein is actually packaged into a fatty body, which we call a liposome. And that is basically the vaccine that gets injected into you. The liposome, because it's a membrane-bound structure, can fuse with your cells once it gets injected. That delivers the RNA into the cytoplasm, which then gets translated into a protein. That protein, of course, would be the spike protein, which then gets transported to the membrane so that it's exhibited in the cell. What happens there, of course, is that the innate cells that we have floating around in the body will recognize that as foreign, and will actually start to break the cells down and start to produce antibodies and T cells against the particular spike protein. And that seems to work really, really well. That's really exciting. Why it's exciting is because this is quick. Nearly all of the other methods that I've got up here depend upon being able to grow a virus in some way or another. And that takes time. With the Pfizer and Moderna vaccine, of course, all you need to do is to synthesize a stretch of RNA, which can be done very quickly. The turnaround for developing one of these vaccines is reputed to be around about 6 weeks. Okay, it's also, and on top of that, of course, you've got to have the clinical trials. And one way that you can speed this process up is actually by doing all the clinical trials at the same time. So normally you might think of the clinical trials proceeding one after the other. So one precedes clinical trial 2, which precedes clinical trial 3. And that will take time, but you can actually circumnavigate that time by actually doing them all at the same time. And that really explains why the Pfizer and Moderna vaccine was the first one we heard about, the first one that went through and got approval. The other vaccine that we had at the time was the Astrazeneca vaccine, and that was based on a viral vector-based vaccine. In the AstraZeneca one, what is used is another virus that has been modified so that doesn't cause an infection. Okay, but it has all of the machinery within the virus itself to actually express a gene. And so what you do is you put the gene that you want to raise the antibodies to into the viral vector, and then that actually forms the vaccine. Now, the viral vector that was used with AstraZeneca was an adenovirus, and an adenovirus for a chimpanzee. This had been inactivated, and because a lot was known about the genetics of this type of virus, it was fairly straightforward to actually slot the gene for the spike protein into the virus, and then grow that up so that you have your vaccine. Okay, so in actual fact, what's both the AstraZeneca and the Pfizer-Moderna vaccines are doing is that they're actually targeting the same thing. They're actually targeting the spike protein. So it doesn't matter which way, all the difference between them is the delivery of how that spike protein was being produced. Since then, another 2 vaccines have been produced based on very similar logic to the AstraZeneca vaccine. This is the Johnson & Johnson vaccine, often referred to as a Janssen vaccine, which has got approval in America. And of course, the Russian vaccine, which is Sputnik V. Now, both of these vaccines use adenoviruses, but the adenoviruses they use are human. Okay, so the Johnson & Johnson vaccine, which is a one-shot vaccine, uses the adenovirus type 26, whereas the Sputnik V vaccine uses 2 human adenoviruses, type 26 and type 5. Okay, so the first injection is with the virus type 5. The second injection is with, is type 26. The second injection is with type 5. Now, why do you use these? Why are you using different viruses to deliver the same gene? Well, it's because antibodies will be produced against the spike protein, but they will also be produced against the virus itself. Okay, so, and that might lower the effect of the second injection. The Sputnik 5 vaccine reckons that if you then give a different virus, the antibodies against that will be ignored, and so you will have a greater immunological response, which seems to be the case from the data that's been produced. And this, of course, also gave the idea of mixing and matching. Because all of these vaccines target the same protein, the argument has been that you can actually use for a second dose any one of these vaccines, and you will actually elicit an immunological response. In theory, that works. I think at the moment they're doing trials to see if it really does work. I can see how the AstraZeneca, Johnson & Johnson and Sputnik V vaccines might be interchangeable. How well they work with other ones is a bit different. Okay, the other types of vaccines that have come on the market are the inactivated vaccine candidates. Okay, and here we have an inactivated or whole-killed virus. Okay, and now there's a number of those that have appeared on the map so far. The first one that came up is produced by Valneva. Valneva is a French company, which strangely enough decided to produce the vaccine in Scotland. So, and the British government has, I think, bought 60 million doses of this particular virus. So this is a virus that actually is SARS-CoV-2, but it's been inactivated. There are other vaccines that are very similar to that. The Sinopharm and Sinovac vaccines are both vaccines from China, whereas the Bharat vaccine is from India, and they follow the same sort of format. The last platform that we see being used to develop a vaccine is where we use or target a subunit of the virus to raise antibodies to. And once again, the main target there is the spike glycoprotein. Now, there's one company here that's actually got further than us, and that's the Novavax vaccine. And that is basically the spike particle. So the vaccine itself is just the spike protein. Sanofi and GlaxoSmithKline are also developing a similar one, but I think that vaccine's been running into a little bit of trouble. And the last knockings, it's just on the news that the government has bought the Novavax vaccine, but GlaxoSmithKline are actually producing it at all places, Barnard Castle, which to English people that should, or British people, that should ring a bell, because that's where Dominic Cummings went for his walk around to test his eyesight out. Okay, so let's have a little bit more details at these new vaccines that have come off. The Valneva vaccine. For that, you need a vaccine. So you need a virus. So you isolate the SARS-CoV-2 virus from a patient, and then you grow that in a laboratory. Now, the SARS-CoV-2 virus will also infect monkey cells. And the cells are often used in laboratories to grow these types of vaccines. They're known as vero cells. And vero cells are the cells from the kidneys of the African green monkey. So we have these in culture. We infect the vero cells with the virus starts to replicate and producing more virus particles. The virus particles are then collected and purified and then inactivated. Now, in this instance, the inactivation process is by treating the viral cells with beta-propiolactone. What this does is destroys the RNA within the virus, making the virus intact as a virus, but not being able to cause an infection. Then to turn this into the vaccine, the adjuvants are added to these viral particles. In the case of the Valneva vaccine, alum is added. This is basically aluminium base, which is known to stimulate the blood cells, and a nucleotide called GPG1018, which is known to stimulate T cells. Okay, so that's the vaccine. The Novavax is a different type of vaccine completely, but it still needs a virus to actually produce it. So here we use another virus that's known as a baculovirus. Now, baculoviruses are not viruses of humans or anything related to animals, to primates. They're actually viruses of insects. And these viruses particularly infect caterpillars, okay, moth caterpillars. So in these are what known as DNA viruses. So we can take our RNA from the SARS-CoV-2. We can read off the spike gene. We can then splice the spike gene into the genome of the baculovirus. We then infect that baculovirus into the moth. Moth then dies, produces exudates. Within the exudates are the spike proteins. Spike proteins are then extracted and then pushed together to form nanoparticles. And it's these nanoparticles that then actually form the vaccine. Okay, in addition to that, the vaccine also contains something called saponin, QS21. Now, that is a plant product from the soap bark tree, which you can find in Chile. Basically, the saponin is a triterpene glycoside, and that is actually quite toxic in some respects, but it does stimulate the immunity system. To lessen its toxicity, it's also mixed with a lipid, and that together with the nanoparticles actually forms a vaccine. So when that is injected into the cells, the nanoparticles are free, they get attacked by the innate cells, which then interact with the T helper cells, which then take those to the B cells so that antibodies to those particular spike proteins can be produced. Okay, so you can see that this type of vaccine has taken a bit longer to develop. Okay, so what's in the vaccines? Well, we've already talked a little bit about the active ingredients, so I'm not going to go through what the active ingredients are because they're all basically the SARS-CoV-2 spike protein. What is of interest is what's used as the adjuvants. We've already seen that in the Valneva vaccine, it's alum and a nucleotide, both of which can stimulate innate cells and T cells. In the Novavax, that's saponin and a lipid, which once again will stimulate the immunity system. Now in the Pfizer and Moderna, what we find that's added with that is lipids, because the RNA is actually bound up within a lipid sac, and another compound called polyethylene glycol. Now, polyethylene glycol is a self-fusing agent. So this actually allows the lipids containing the RNA to fuse with your cells inside. Okay, so those are what's in the adjuvants. Residual traces, acetic acid and ethanol, I think, is in very small parts are present. The preservatives and stabilizers mainly contain things that can control the pH of the solution. Tromethane is a buffer. Histidine, which is present in the Astrazeneca vaccine, is also a buffer. There's also stabilizers within the mixture as well. Polysorbate is a stabilizer of viral structures, so that's included in both the Astrazeneca and the Johnson & Johnson vaccine. Cyclodextran is a compound that actually improves the solubility of compounds. So that's actually added to the vaccine to improve its solubility. Pfizer also contains sucrose and inorganic salts, including phosphates. So that's basically what's in the vaccine. Now, because we need to know something about these vaccines, and nearly all the ones that have been approved have gone through their clinical trials, and they have different amounts of efficacy. Now, what I have seen a lot on social media and stuff is saying that the Pfizer and Moderna has a 95% efficacy. Therefore, it is better than the Astrazeneca because at best that only has 70%. Unfortunately, you can't compare efficacies like that. The simple reason is because they come from different populations that have been used to gain those figures. So those figures are really not comparable, and the efficacy can change. It very much is dependent on disease prevalence. So if there, for instance, if there isn't a lot of infection around, then you might well find that you have a very high efficacy. If, on the other hand, you do your clinical trials when there's a lot of the infections around, then you'll find that your efficacy might be diminished in somewhat. So it's wrong to compare the efficacy to say one's better than the other. What we're looking at here is that we have around 70% efficacy from the trials that have been done. Okay, now because that means that we, as we've already seen from our calculations, that then we have a chance of actually gaining what's known as herd immunity in the system. Okay, so these are the efficacies that have been published down the line. Now, the clinical trials that are done are usually defined treatment regimes. Most of these doses are given usually with about a 3-week period. So one dose is given, then 3 weeks later you should have your second dose. Why have they done that? Well, I suspect the reason why that regime was picked was speed, was to actually get these tests done as quickly as possible. So if you left it any longer period of time, then between the doses, then that would have actually dragged out the time for when the clinical trials are being done. So I suspect this is the reason why we're looking at this 2-week period, 3 week to 4 week period between jabs. The Astrazeneca vaccine has actually looked at jabs given after 12 weeks in trials, and they found that the efficacy value fell from 70% roughly to about 67%. So not a big difference, still usable. That incidentally was done after the government announced that it was going to delay giving the second jab. What efficiency there is in these things, well, we won't really know until the vaccines have rolled out. Where we've got the best estimate so far is in Israel, where I think well over half the population have fully received the vaccine. You're not really vaccinated until you've received both jabs. And what they noticed there was that the efficacy or efficiency was about 30% after the first jab, that rose to 94% after the second jab. So we can see that the Pfizer vaccine is actually, it does what it says, more or less. As time goes on, then the efficiency, the real efficiency of the vaccines will become apparent. And of course, we will expect might well be some changes, because in this case, we're actually looking at the natural population, and that will consist of well and sick patients. Trials, of course, are usually healthy patients that are divided up into those that receive the vaccine and those that don't, and then looking at how they respond to whether they get infections or not. Okay, so we've had a look at the vaccines. Now the question now is do vaccines have adverse effects? And my answer to that is yes. All medicines, in one way or another, have adverse effects. But are they serious enough to not use a vaccine? There are certain areas that we're interested in here, obviously, with people with heart conditions, people with allergies, immunocompromised individuals, and females that are pregnant or breastfeeding. These are and what the effects the vaccine might well have on the unborn child. These are all people that we're particularly interested in knowing something about. We can break the effects down into those that are quite common, that perhaps happen 1 in 100 doses, those that are less common, those that happen to 1 in 100 to 1 in 100,000, to the rare, which happens to about 1 in a million, 1 in 100,000 to 1 in a million. And then ones that we really don't have enough information on to really come to anything sensible. So the common types of adverse effects that we have, and this is true for all of the vaccines that have been tested so far: flu-like illness, fever, headaches, dizziness, chills, weaknesses, tiredness, aching muscles, nausea, rapid heartbeats. These have all been recorded as, if you like, side effects of having the vaccine. Should we be worried about these? Not really. They usually pass within 48 hours or so, 2 days, and then you go back feeling okay. When I had my jab, I didn't feel anything. It makes me wonder whether my immunity system's working, actually, but normally the rest of my family certainly didn't feel too good after having the vaccine, so that's fairly common. You shouldn't be worried about those. Actually, all of these side effects are, if you like, measures that your immunity system's actually working. Allergic reactions and coagulation disorders. Now, I want to spend a few minutes looking at the coagulation disorders because that's something that's affected certainly the Astrazeneca virus, vaccine. So, where it's actually been suspended from use in some European countries and in Canada, and its been used has been recommended for perhaps older people. So, does the vaccines cause blood clotting? Now, I think really, if you're going to answer this question, the first thing you have to know is, well, what is the incidence of blood clotting in a normal population, so that you can see whether the vaccinated population is increased or not. And then you have to look at the vaccinated populations to see what the incidence is there. And you have to be able to compare the vaccines as well. Now, the incidence of blood clottings in natural populations occurs at about 1 case in about 1,000 individuals. Okay, so that's about 0.1%, which is worth bearing in mind as we go through this. So what is the incidence of blood clotting in the vaccinated population? Now, in the UK, we have a system that's called the yellow card. And the yellow card system documents all of the adverse effects that have been noted with a particular treatment. We can actually look at these. These are available on government sites, and they're known as the COVID analysis prints. And they give off all the different types of symptoms that have been noticed after vaccination. And we can see that the reported number of clots in the UK, according to these reports, is 99 individuals for the Pfizer and 96 for Astrazeneca. And that is out of a total number of reports of 100,077 and 100 for Pfizer and 228,774 for AstraZeneca. Okay, so just looking out of those are reported, that's coming close to the 0.1%, less for the AstraZeneca. If we look at the total number out of that percentage out of the vaccines, then it's way below 0.1%. Even if we add them both together, the value still comes up at below 0.1%. So on this value, one would say that there's not a lot of evidence there to suggest that any of these vaccines are causing blood clots. But perhaps we're missing the point here. So just by looking at this, might be missing a particular type of blood clot. So we need to look at the proportions or the numbers of different types of blood clots that have been produced by the different vaccines. And what we can find there is that we can use the yellow card information that's produced in the prints, and we can look at what numbers. Now, what I've done here in this table is picked out the numbers that have been reported for up until 25th of March. And in this line here, I've put the frequency that's expected. Okay, so we can look at venous thromboembolisms, VTEs. This includes deep vein thrombosis and pulmonary embolism, thrombosis. And we can see that there's a number of those that have happened, but the numbers really are similar between both vaccines. And really, they don't break the level of 1 to 2% per 1,000 individuals. That is also true of non-specific embolisms and non-specific thrombosis, and even the hemorrhages. Okay, so why did a number of countries decide to suspend the Astrazeneca virus? And the reason for this is because of these types of thrombosis, the cerebral sinus venous thrombosis, or CSVTs. Now, in the UK, we noticed 3 of those per 200,000, 1 per 100,000, very similar between Pfizer and Astrazeneca. Doesn't really come up to the 1.35 per 100,000. This, incidentally, is a new estimate of the frequency of these within populations. Now, the reason why this is particularly was a problematic was from reports that came out of the Paul Ehrlich Institute in Germany. And what they noticed was that there was a far greater increase in these people that were suffering from these types of thrombosis than what we're noticing here. At present, in Germany, there are 31 cases of CSVT for, I think, 2.7 million vaccinated. Okay, so this is actually getting higher. That's literally basically one case in 87,000 people. So we're actually getting higher than this value. Okay, that's purely in Germany. In France, the values are very similar to this. In Norway, the values are very similar to this. Now, one of the things that has been linked with this type of thrombosis is a disease or a complaint that's called thrombocytopenia. Now, this isn't necessarily a thrombosis. What it is a fall in the number of blood platelets. Now, there are a number of reasons why this can happen. Some of them hereditary. But what was noticed in the German report was that people that suffered from CSVT, also a significant number of them also had thrombocytopenia. Okay, so I've included this within the UK studies, and we see that really the values here are well below what we might expect of for the natural occurrence of this within the population. What can cause thrombocytopenia? Well, the things that were picked up by the German scientists who are studying this was that what they picked up was specific antibodies that will attack the blood platelets. Because the antibodies are attacking the blood platelets, that will form a clot. And the argument is that that clot seems to happen primarily in the brain. That's quite a dangerous situation. Now, the interesting thing with this is that the majority of the people that are suffering from this in the German study have been females. Now, I've shown this value here of what we expect in a normal population of 1.3 per 100,000 people. That's a raise, because before that, it was thought to be 1 perhaps in a million plus. This study, which actually stated that the incidence is actually much higher than normally thought, also pointed out that females were more inclined to have this, particularly those that have been on oral contraceptives. So there is a link there between that and perhaps developing this. Even so, this is still quite a rare event, and CSVT is actually easily treated. At the moment, the advice given for that is that if you have headaches that last for more than 4 days, seek medical advice after receiving the vaccination, within 2 weeks of receiving the vaccination. Okay, so possibly, were the Germans right to suspend it? Possibly. I think if you have something that looks as if the numbers are above what you'd expect, then yes, you should pause and have a look. That doesn't seem to be the case in the UK, however. What about allergic reactions? Well, yes, there's been some allergic reactions. Roughly, I think for the Pfizer, there was about 11 cases per million vaccines. The proportion of these are actually relatively quite small. The compounds that they've been linked to is the polysorbate in the Astrazeneca virus and polyethylene glycol. So if you have, if you know that you have reactions to those, then you should not be vaccinated. If you're wondering what polyethylene glycol is, well, ethylene glycol is what's found in antifreeze. So if you've been putting antifreeze in your car and you've developed a reaction to that, then probably you shouldn't have a vaccination. Immunocompromised individuals, not enough information at present. Pregnancy, breastfeeding, there's no information of risks for pregnant or breastfeeding women to not have the vaccine. And it's also been recommended to be safe for people with heart condition. So these two things taken together, it's not too surprising that the World Health Organization have reckoned that the Astrazeneca virus vaccine is safe to take. Do they have long-term effects? Well, it's too early to say about any of these vaccines, whether they have any long-term effects. In the past, of course, there have been effects with vaccines. Some of them due to poor standardization. So where perhaps where we've been using, particularly in the yellow fever vaccine in the 1920s, the virus wasn't properly inactivated. In those days, of course, there wasn't the regulation that there is these days. And these days, quality control is actually everything. So we'll wait to see what happens with the vaccines. Although, to be honest with you, I don't see any real long-term effects with any of these. Why get vaccinated? Well, vaccines work. And even now in Britain, we can see that the vaccines have worked. If we look at these two figures here, this is taken from the Financial Times, we can see that both the hospital admissions of those aged 85 and above, which have been those that have predominantly had the vaccine, has dropped. And it's dropped more than those aged 16 to 64. Okay, so in both cases, the hospital admissions is greater for those aged 18 to 64 or from 0 to 69 than it is for the aged 80s, 85s and above, which is amazing. I mean, that you don't expect that. That is the vaccine effect. So we can see already that the vaccine is having an effect and that it is preventing deaths. So that's a very good reason to get vaccinated. The other reason to get vaccinated is that COVID is actually deadly. If we look here, this is a plot of all the different types of viruses that are around. And we're plotting here the death rates against the R values, the infectivity values. COVID actually comes around the same level of Spanish flu. And why public health scientists were really worried when this first came on the map was because the other coronavirus virus infections, SARS and MERS, are certainly much more deadlier. So this could have developed into these are very similar viruses. COVID-19 is not the flu. It's not a cold. It's far worse. Fatality rates are between 1 and 3, but this is an average. And the trouble with this is that some groups actually have greater have a greater death rates. For instance, those above 80 in care homes, the death rate could be as high as 30%. COVID, the virus SARS-CoV-2 can be transmitted asymptomatically. That is something we know very little about of why that might be. The other reason, of course, is if you get infected by SARS-CoV and you develop COVID-19, you can develop what's known as long COVID, which are long-term health effects as a result of the infection. And a paper just published today reckon that was around about 1 million people in the UK at the moment are suffering from long COVID. Third, you stop new variants forming. If you can stop them replicating, then you stop new variants replicating. One of the worst things you can do is to let a nasty virus replicate in the population, because if it replicates in the population, it can become adapted. Natural selection will ensure that it becomes adapted to its new host. And this is what we've seen happening here. There are 3 lineages at the moment that are particular concern. One was in the UK, which has developed mutations that actually improve the binding of the virus to the target cell. Okay, this not only improves its transmission, but data recently has shown that it's also made it more deadly. Okay, and of course this virus now is widespread in America, widespread in Europe, and causing the 3rd wave of infections in Europe. The other 2 variants that we're worried about is the South African variant and the Brazilian variant. And these are very similar to the UK variant, okay, but have happened independently. And I'm afraid this is what happens when you let a virus replicate. The countries that have done well out of this, of course, are the countries that have actually allowed their public health scientists and workers to take charge of the pandemic and not left it in other hands. Okay, so this is actually a graph of maps of all the different types of lineages that are present in the world at the moment. Each little dot, it's a genome, complete genome analysis. Each little dot here represents a different lineage. And we can compare these together to produce a tree. This tree is based on genetic differences. So we can see that these evolution in action, actually, these are becoming very different to the main bulk of the other lineages. Just to give you some more information, if we look at the 4 lineages, because there's a second Brazilian one, P2, they all share the same mutations, and it's these mutations that actually cause the spike protein to interact better with the receptor protein so it can gain entry into the cell. The vaccines, well, the vaccines work well with the UK variant. They don't apparently work so well with the South African and Brazilian variant. And this is a worry, because if we don't actually shut down the viral growth fairly quickly, these could actually take hold and expand. As these are being killed off by the vaccines, these might well then go in to take its place. The governments have already warned that there may well be booster jabs, and Moderna are certainly starting to develop new vaccines for the South African and the Brazilian variants already. So when they say that there will be boosters in early autumn next year, I believe that might well be true, and it may well be true because we're going to be fighting these other variants that have come about. Fourthly, and I'm going to pull it up because I've gone over my time quite dramatically. I can see Laura looking quite worried there. The pandemic is not over. Here's a map of Hampshire, and we can see that yes, some areas the drops have gone down, but some, including Portsmouth, it's going up. Yes, Southampton, although it's gone down, but it still has a higher average than the rest of England. So this isn't over. Just because we got 40% of the population having one vaccine or whatever, doesn't mean to say that it's over. The other worrying thing is take-up of the vaccine. And this shows a map of Birmingham. And what we can see here is that, yes, some areas have been very good in giving vaccines to the over 70s, 100%. But look at this. There are areas there where people haven't actually refusing to have the vaccine. And that's a real worry, because if you have pockets in the population that are sensitive, then the virus will still grow, it will still be able to mutate, it will still be able to produce other variants. Two last things very quickly before I go. Worrying things about the English variant. This was published in December. And what we can see here is an increased infection of those under age 19 and under. Okay, this was published in December, and I suspect it was this information that made Boris Johnson shut schools. Because the worry here is not necessarily that the younger people are more prone to this. We know where this ends. We know that this ends in actually passing this to the more vulnerable people. And that's the worry. And that's why Boris Johnson closed schools down. It's not over. You can see this is more recent data where we started to open schools. And within the 5 to 15-year-olds, we can see that the rates are actually increasing. So all good reasons to be vaccinated and to still keep your distances. Don't think it's over, it's not. And for that, I shall stop because I've gone way past my time. I do apologize, and thank you for staying the course. I'm willing to take questions and talk a little bit more about the new variants if anyone's interested. I've got some slides on here if anyone's interested in that. But thank you for listening and thank you for your attention. And thank you, Laura, for inviting me again.
No problem. And thank you so much. I feel it was very thorough, and I'm sure people will forgive you for going over on that basis. It was so interesting. I'm going to stop recording.
Hello again. I've added an addendum to my talk because immediately after, in fact, the next day after I gave my talk, the government produced figures on blood clotting in patients after they've received the Astrazeneca vaccine. And these figures were different to the ones that I showed during my talk. So I thought it would be a good idea to actually give those figures now, explain the differences between the two sets of figures, and perhaps explain a little bit more about how blood clots actually occur within bodies. In addition to this, I've also included some figures on mortality rates around the world and how the trends have changed according to government policy towards a pandemic. Before I look at the data that the government has published recently on the effects of blood clotting and the Astrazeneca vaccine, I want to spend a few minutes talking about how blood clots form in the first place. I think as we go on, you'll see the relevance of why I'm talking about this in a bit more detail. Okay, so what is a blood clot? Well, a blood clot is just a collection of blood cells and blood platelets that are stuck together to form a sort of plug. And normally this plug is used to stop the loss of blood when you get injured. So if you cut your finger or have a cut anywhere, you will notice that eventually the cut will form a scab, and that scab is actually as a result of the blood clots being formed around to stop the blood. So it's an essential part of our interactions with the outside world. Unfortunately, blood clots can also happen with either internal injuries or for other reasons as well. And when this happens, of course, the clot, or plug if you like, actually starts to block veins and arteries. And when this happens, your blood circulation level actually drops quite a lot. And of course, this actually can be quite dangerous because your body isn't getting the blood that it needs. In its most extreme cases, of course, these blood clots can actually travel to the vessels in the brain, causing a stroke, or they can travel round to the heart and stop the heart from working. And both of these are very serious complaints indeed that often lead to death. So keeping an eye on how your blood clotting is going on in your cell is actually quite an important aspect of checking your overall health. So how do these blood clots form? Well, to be able to form a blood clot, you need something that's going to stick all of the cells together. And that substance is called fibrin. And fibrin is produced from the blood platelets. Okay, but blood platelets don't always produce fibrin. Obviously, you would, if they did, then you'd have big problems with your blood clotting all the time. So normally, blood platelets circulate in the body in an inactive state, and they have to become activated to start to produce the fibrin. The mechanisms of activating blood platelets is actually quite complicated. There's more than one route, as you might expect. And of course, this leads to the problems that sometimes we have with blood clotting when there's no real signs of injury anywhere. So activation of the blood platelets is the first step that's needed to generate a blood clotting mechanism. Now, I mentioned that we need to produce a sticky substance. This sticky substance is called fibrin, and that is produced from another substance called fibrinogen. Okay, so fibrinogen is converted to fibrin, and for that to happen, we need another substance called thrombin. And thrombin is also produced via the platelets reactions. Okay. Now, just as we can have a substance, the substance fibrin produced as a result of the activation of the blood platelets, we also have other substances in our body. One of these, which of course is called antithrombin, which actually lessens the production of thrombin. Okay, so we have a series of mechanisms that can control whether fibrin is going to be produced or not. As soon as the blood platelets become activated, they start to release a protein that is called blood platelet factor 4. And this protein actually binds to the antithrombin substance and prevents the antithrombin substance from functioning. Okay, so it cuts out the antithrombin side of it, which of course allows more thrombin to produce. As more thrombin's been produced, then we got more fibrin produced. And so that's basically, in the simplest term, how the blood clotting mechanisms works. Now, there are a number of ways in which you can trigger the activation of blood platelets, and we'll talk a little bit more about that when we look at sometimes what goes wrong. Now, some people suffer from forming clots, and when they do, medics often give them a substance called heparin. And what heparin does is stimulate the production of the antithrombin. Okay, so this will actually make the blood less sticky, and therefore less chance of forming a clot. One of the conditions that have been linked to vaccine-induced blood clots is thrombocytopenia. So what is thrombocytopenia? Well, it's actually a recorded loss of blood platelet numbers in your blood. And of course, this is quite a serious condition. Now, you might think that if you have a reduction in the number of red blood platelets, then the chances of you actually having a blood clot might well be reduced, because there aren't the blood platelets there to actually initiate the clotting process. And you'd be right. Why this is a serious condition is because people that suffer from it can have uncontrolled bleeds, which is a very serious condition. So how does a condition that reduces the formation of blood clots be linked to a situation where the risk of blood clots is increased? Well, to answer this question, you have to look at the mechanisms behind how blood platelet reduction takes place. And at present, there are about 3 different mechanisms that exist that will reduce the blood platelet numbers. The first of these is called sequestration. And here the blood platelets stick together so that their numbers get reduced out. Now, this is a rare condition that's usually associated with an enlarged spleen. Okay. The second mechanism whereby the number of blood platelets is reduced is where we have a decreased production in the number of blood platelets. Blood platelets are formed in the bone marrow. So any diseases of the bone marrow that limits the production of blood platelets will reduce the number of blood platelets in the blood. What we find is that usually the bone marrow uses cells and it sheds off these smaller anucleate cells which enter the bloodstream, which then become the blood platelets. Okay. So any diseases or disorders that will affect that will lower the number of blood platelets in the blood. Conditions that can mimic that, of course, include things like vitamin deficiency. Deficiencies in vitamin B12 or folate have been recorded to show that there's been also a decrease in blood platelet numbers. Drugs, toxins can reduce the number of blood platelets in the system, as does radiotherapy. All of those can reduce the number of blood platelets in the body, as well as can infection. And now there have been a number of viruses, bacteria, and fungi that, when they've caused infections, have resulted in lowering of blood platelets. And this includes SARS-CoV-2. Now, with SARS-CoV-2, the blood platelets also contain the ACE2 receptor on their cell membrane. So they are susceptible to being infected by SARS-CoV-2. And this may well lead to the reduction in the number of blood platelets that we see that might well be associated with a SARS-CoV-2 infection or COVID-19. The third mechanism that is used to cause thrombocytopenia is where the blood platelets are destroyed. And there are two main mechanisms that are in operation there. The first one is a non-immunological reaction, such as you might find with anemia. So in anemia, you might well have a destruction of blood platelets as part of the disease. The second mechanism is an immunological one. It's where maybe there will be antibodies that are formed against the blood platelets, and this will lead to their destruction. Now, this reaction, of course, is one of the reactions that could lead to blood clotting. But why should reduction of blood platelets lead to blood clotting? Now, an explanation of how that can happen is looking at a rare case which is involved immunological reactions when we have a drug-induced thrombocytopenia. And such a case of that is where we have the blood thinning agent, heparin, where heparin induces thrombocytopenia and includes increased levels of blood clotting. And we'll talk about that next. So what is heparin-induced thrombocytopenia, and how is that related to blood clots that may be formed after vaccination? It's long been established that patients that have received heparin in order to make their blood less sticky sometimes can develop antibodies that are effective against the platelets that are involved in forming blood clots. And that as a result of this, sometimes, counter to what you might expect happen, blood clots develop. So let's have a look at the mechanism for this, because it's believed that it's a similar sort of mechanism that might be going on after vaccination to generate blood clots. When the blood platelet cells become active, they actually start to release the platelet factor 4, which is a protein which binds to the cells and inactivates antithrombin. Now, sometimes the heparin and the proteins of the platelet factor 4 interact together to form a complex. Now, why they form this complex isn't fully understood, but some people think that it might be due to the large negative charge that's on heparin. And this allows an electrostatic relationship to exist between the protein and the heparin to form the complex. Now, the body actually recognises this complex as foreign, and that's picked up by the innate white blood cells, which then will engulf it and then produce antigens based on that, from which T helper cells will take to B cells so that antibodies against the complex can be formed. So when this happens, the blood then starts to contain antibodies against the heparin platelet factor 4 protein, okay, and they interact with it, forming another complex with the antibody. This complex then interacts with the blood platelets themselves, and it can also interact with cells of the epithelium of the blood capillary. Now, when this happens, the blood capillary takes this as a sign of damage and starts to release what's known as the tissue factor. Now, the tissue factor is one of these alternative routes to actually start producing thrombin. So as a result of that, thrombin is started to be produced. The activated blood platelets now also start to produce microparticles. So these, together with the fibrin that eventually is produced, will then start to bind red blood cells, forming the clot. Okay, so this is how we can have the blood platelet numbers falling, and yet we still have blood clots forming. Now, I have to point out that this is quite rare. It doesn't happen for every single person that's taking heparin, but it can happen, and we can detect it by looking for the antibodies themselves being produced. These are often referred to as the anti-D complexes that are discovered. Once we do that, once we can detect that, of course, we can then give the patient drugs that will actually break up the clots and prevent further damage being done. So how does this link in then to blood clot formation after vaccination? Well, there are some thoughts there that what's happening is a similar process, but this time something to do with the vaccine itself. So that's either the spike protein that's being produced interacts with the blood platelet 4, or it's perhaps the viral vector that's interacting with the blood platelet factor 4 to form a complex which then is recognised as foreign, which from then we get antibodies produced, and we have a similar sort of scenario where the antibodies with the viral factor plus blood platelet factor 4 cause production of the tissue factor, which then actually starts producing thrombin. From that, we can then start to get fibrin and the micro particle producers from the platelets, so that blood clots can form. So the mechanism is similar. Why do people think that the mechanism is similar? The reason is quite simple, is because scientists in Germany and in Norway detected the antibodies that will fight against, if you like, the heparin-induced antibodies that are produced. So those have been detected. And the only way that they can think of that happening in the absence of heparin is if there is some aspect of the vaccine that's actually generating that. And so this is why people think that in a very rare cases that after the vaccination that some blood clots could form. In the talk, I gave you data from the published, yellow card published vaccine analysis prints for both the Astrazeneca vaccine and the Pfizer vaccine. And I've put those up on the screen here. Now, if you add these up, you can find that there are 43 cases of thrombocytopenia with one fatality for the Astrazeneca vaccine, whereas there are 23 cases of thrombocytopenia plus one fatality for the Pfizer vaccine. So from this data, we can say that both vaccines can induce thrombocytopenia. There are slightly more cases for the Astrazeneca vaccine than for the Pfizer one, but that may be down to the sampling error. If you think that the number of people that have been vaccinated are somewhere in the region of 18 million or so plus, then these numbers represent a very small proportion of people that actually develop these conditions. If we look at the thrombosis and embolisms that might have resulted from after vaccination, then we find that for the AstraZeneca vaccine, there were 41 cases of thrombosis of all different types, with 3 fatalities. Whereas for the Pfizer one, there were 45 cases of thrombosis, all types once again, with 2 fatalities. So once again here, the numbers look very, very similar. But this changed when the government published new figures. The data produced by the government regarding blood clots and thrombocytopenia after vaccination are shown in the table. These were produced after I gave my talk, and the data here shows the number of blood clots suffered with thrombocytopenia after AstraZeneca vaccination up until the end of March. Recently, the MHRA released data on this up until the 30th of April, and I've included this information with the numbers are shown in brackets. So the numbers without brackets are the numbers that are present up until the end of March. The numbers in brackets are those present up to the end of April. Now at the end of March, the total number of thrombosis with thrombocytopenia was 79, which increased to 209 by the end of April, with 41 fatalities. Now, although this seems to be a large number, it is out of 27.6 million people that were vaccinated. And this represents approximately 1 case per 132,057 vaccinations. Now, this number is close to what we might expect without vaccination, i.e. the number of people that develop these conditions without being vaccinated. And this is estimated to be approximately 1 per 100,000. Given this number, we would expect 361 people to suffer with blood clots with thrombocytopenia out of the 27 odd million people that were vaccinated. So the blood clots are indeed very rare events. Now, from this number as well, it appears that a greater number of females suffered from this condition rather than males. Here we see 120 females had a thrombosis with thrombocytopenia after vaccination, whereas only 89 males suffered a similar condition. This difference between the sexes, though, could be just a statistical variation due to chance. We're dealing here with rare events and very small numbers, and in these situations we can often have a slight bias which isn't representative of really what's happening. So one has to be careful one looks at that to say that females are more sensitive. They might not be. It might be down to sampling error. The other thing to notice from this data is about a third of the people that developed the thrombosis with thrombocytopenia were under 50. And of course this actually raised concerns within the government about what they should do with this, and led to them thinking that they should only recommend the Astrazeneca vaccine for people over 60. Okay, so when we look at these figures, they do seem to be something that is real, but should we worry about it? And how do we judge this as a risk factor? Judging rare events as risk factors can be very difficult because there are maybe many things that actually influence the risk. One of those things might well be what is the risk of having a thrombosis with a vaccination compared with what's the risk of having a thrombosis due to an infection of SARS-CoV-2. And in the table I've also included data that shows the incidence of thrombocytopenia and the incidence of deep vein thrombosis of patients that are suffering from COVID-19 that ended up in intensive care. And we can see that of those people in intensive care, 36.2% of them developed thrombocytopenia and 28% of them developed deep vein thrombosis. On top of that, 7.8% developed a pulmonary embolism, and 1.6% actually had a stroke. Now these figures are much higher than those that have been reported for having a blood clot after vaccination. So if I was given a choice between having a vaccination or catching SARS-2 infection, I would choose. As a result of publishing the numbers of patients that had a brain blood clot with thrombocytopenia after having a Astrazeneca vaccine, the government decided to limit the use of the Astrazeneca vaccine so that it would only be given to people over 60 years of age. So why did they do this? What was the logic behind making this decision? Well, their decision was a cautious one, which was actually quite proper. But it was based on a study that was done at the Winton Centre at the University of Cambridge, where the Winton Centre performed a risk analysis of people becoming ill, particularly with blood clots, in non-infected populations and infected populations. Okay. Now, making a risk analysis of rare events is actually quite a tricky thing to do, and you have to bear in mind a number of factors that could influence this. In this case, what they were doing was comparing the risk of having, say, a blood clot on the brain normally without vaccination, compared with those with vaccine after vaccination, and with those that actually had a SARS-CoV-2 infection. The graph that you can see on this page actually shows the mortality rates across the different age groups and for the different sexes. And we can see from this graph that the mortality rates obviously increases with age. That should be no great surprise. There is a slight difference between males and females, with males slightly higher rates than females. The mortality rates due to COVID infections are shown as the black circles. And what becomes immediately or abundantly clear from this graph is that people aged below 30 have a far less mortality rate after COVID infections than would normally be expected. Okay, whereas in people aged over 60, then the chances of the mortality rates actually increase with COVID infections. Okay, so this was a deciding factor in publishing risk factors associated with the Astrazeneca vaccine. The risk analyses performed by the Winton Centre at the Cambridge University are shown in the three figures on this slide. Here they show the potential benefit against the potential harm caused by vaccination in three scenarios for different age groups. And the scenarios included the risk of exposure. Okay, so there are three groups for the three figures. The first one is for low exposure to the virus. This might be people that are at home, that don't enter into crowded situations much, and one would consider them to be low risk. The second group is for the medium risk of exposure, and these might include people that routinely have to work in environments where there are crowds. And the third scenario is where the risk of exposure is high. So this would be for people that work as nurses, or in the medical field, for doctors, for carers, and perhaps for teachers as well. So these are the three groups that were compared across different age groups. The graphs or the data for the set of individuals in low-risk environments shows that the potential advantage of having the vaccine far outweighs the potential harms of having the vaccine, except within the groups of that is under 30. And for these people, the risk of harm is slightly greater, but not by much, than the benefits acquired from vaccination. In fact, I would say that it's closer to almost equal distribution. Okay, but this is the only group. If we look at all the other figures on there, for all age groups, including the under 30s, in medium exposure risks and high exposure risks, the benefits of vaccination far outweigh the potential harm that is caused or may be caused as a result of vaccination. Do lockdowns work? I thought I'd spend a few minutes talking about this because there have been some incidences of people actually saying that they don't work. Well, if you think about it, of course they work. Viruses themselves have no locomotion. They can't track down their host target victim. The only reason you get a viral infection is because you enter into an environment where there's a high viral load, and you can pick that up. Now, in the case of aerial-borne viruses, that happens to be in the air. So if you enter an environment where virus particles have been discharged in the air, then you're highly likely to get infected. Obviously, if you limit your exposure to these high-risk environments, you're going to limit the chances of you being infected. So from this point of view, a lockdown where you are asked to stay at home and not to go into crowded places and to limit your interactions with other people, of course it's going to lead to a reduction in the number of infections. I don't think you need a degree in astrophysics to work that one out. Nevertheless, people have claimed that lockdowns don't work, including actually our Prime Minister, who very early on in the infections stated that it was doubtful that lockdowns work. Well, most public health scientists disagree with that, and I think what's happened since has borne out the fact that lockdowns actually do work. So let's have a look at some of the data. And what I've put on here are 3 graphs showing the mortality rates over last year for 3 countries that had very different approaches to lockdown. First one on the right is of China, which had a very strict lockdown. Here, transport or travel between different cities was completely blocked. People had to stay at home. They were forced to stay at home, in actual fact. I had a friend who lived in China who couldn't even go out and do shopping. The shopping had to be delivered to the house. That's how strict the lockdown was. That lasted for about 3 months. And as you can see from the graphs, that almost eliminated, well, it eliminated the virus from China. The cases you see now of occasional cases of COVID-19 in China have occurred as a result of migrants, of people coming into the country from other countries where the infection rate is higher and bringing it with them. But in China, they had a very effective track and trace system, so that as soon as they detected an outbreak, then that whole area was shut down and people were traced and isolated. And that seems to have worked. Okay, if we move on to the middle graph, that shows the United Kingdom. And you can see in the early stages of last year, there was a rise in the mortality rate, which linked into the first wave. Then late in April, the lockdown procedures were put in place. And we can then see that as a result of that, the travel between cities was reduced. It wasn't totally eliminated, but it was reduced. And this actually caused the exposure of people to higher risk areas was reduced, and therefore the mortality rate came down. Where that was different, of course, was in hospitals, and as we already know, most of the severe cases of mortality happened for people that worked in the health services. Britain didn't really close its airports down, so we were still importing variants from different parts of the world into the country. And we were very slow to implement track and trace, despite spending an enormous amounts of money on it. Okay, but we can see from the graph that it did work. We then, in the summer of last year, stopped the lockdown. And as we can see that as we stopped the lockdown, because our track and trace system wasn't working very well, the number of infections increased quite dramatically. And that eventually led to what we saw at the beginning of this year in January and February, where there were even higher levels of mortality rate. Okay, so once again, that's come down because track and trace was put into place, and that has, along with the vaccine, has actually lowered the number of cases in the UK. Okay, so here we can see that visibly track and trace, the lockdown does work. In fact, that actually fulfills the need to see what happens when you don't have a lockdown. What happens? Okay, if we go on to the third case, which is over to the far right, and that's of the USA. Now, in the USA, the government of the USA didn't introduce a lockdown system that was nationwide. It allowed different states to implement what lockdown they wanted. And some states didn't introduce any lockdown whatsoever. So you had a very mixed response to COVID-19 in the USA. Some states closed schools, some states left schools open. Airports weren't closed, people were still coming in from different countries. I think the government at that time did block entry from certain countries like China and Europe at some points in time. But what they didn't block was actually Americans coming back from those countries. And of course, those people can actually bring the virus with them. As I can work out, the track and trace system in America hasn't really worked very well. Despite the huge resources that America has, their sequencing of virus genomes was quite poor. And as we can see from the graph, there was, in essence, very limited lockdown in place, which meant that the mortality rate stayed high throughout the whole year, resulting in 500,000 people dying. If we compare that to the UK, where we had 130,000 people dying, yes, we suffered, but in China, the number of people that died was actually a lot lower. Okay, so from this, I can say that there's a pretty good evidence that lockdowns do work. Now, okay, you can criticise me that I cherry-picked some data. You know, I've chosen China, which is the strictest, and the UK, which perhaps wasn't the best, but did have a lockdown, and America. If we flick over to the next page, or the next slide, you'll see that I've put up a number of other mortality rates over the years. And we can see that in every case, the countries that actually didn't introduce a lockdown suffered greater mortality rates than the countries that did. I think that speaks for itself. The one thing that can threaten the success of the vaccines we're currently using are new variants of the virus. And particularly if these new variants are not receptive to the antibodies that the vaccines have induced. In which case then you can have a subset of viruses that even if you've been vaccinated, the antibodies that you have generated as a result of that vaccine will not fight off the infection. So you can acquire a COVID-19 infection. And in those cases, of course, those variants will be selected for, because we have vaccines that work against the other types of SARS-CoV-2, and they will become common, and then we will enter into a situation where we will have another lockdown, or we will have another series of waves of viral infection. And this is actually to be expected. To think that the virus will stay the same is mistaken. We all know that viruses replicate, they mutate, and it's within these mutations, some of which may well be improve the infectivity of the virus, some might not. But we know that we have a selection in operation, and those that actually are successful at infecting people will be the viruses that are then spread to other people. So we can see that these viruses will indeed be selected for, and they will replace the other types of viruses within the population. We've already seen this happening. We've already documented variants that are generated around the world, including our own, rather shamefully. We have our own UK variant, which is more transmissible and potentially lethal than other forms of the various. The generation of these, I say, it shouldn't be a surprise. It's actually evolution in action, and it's the virus adapting to its new host. As a virus emerges, as it jumps from one host to another, there will be a series of mutations that will be selectively favourable as the virus adapts to its new host. And we see this happen time and time again. So this shouldn't have come as a big shock. At present, we have a number of variants that are quite worrying. I've already mentioned the UK one. Thankfully, the vaccines that we're using at present are active against the UK variant, B117. So that's good news. Unfortunately, they're less effective against the South African variant, the Brazilian variant, and the Indian variant. Now, if we look at the genotypes of these, and I've put up a table here of just the mutational changes within the S gene. There are other mutations in other parts of the SARS-CoV-2 genome, but I'm just focusing here on the S gene. And what we can see is that there's a series of mutations there, starting off with a mutation that changes the amino acid residue at position 501 in the S protein. Going on to changes in mutations at position 484, and both of these types of mutations have actually improved the binding of the S protein to the ACE2 receptor, and this has meant that the virus is actually better at spreading and potentially more dangerous and lethal than the previous variants. We can see that in some instances in the British, South African and Brazilian variants that there are some of these mutations in common. Rather worryingly, in the Indian variant, the mutation at amino acid residue 484 is a different type of mutation, and that has actually increased the transmissibility and the infectivity of this particular virus, the Indian variant. So we can see that yes, the virus is changing and it's actually becoming more transmissible and potentially more deadly. So it's really important that we actually limit this down, the spread of these variants down as much as we possibly can, which often might well mean more lockdowns. There's no real way of getting that until a vaccine for these variants is produced. On the good news front, Moderna have already said that they've started work on developing vaccines for these variants, which is good news, which we should see coming, being around perhaps towards the end of the summer into autumn. And that coincides with public health scientists saying that they expect booster vaccines being produced around about that time. And I suspect this will be for these variants that will be present. They're already present in the UK. At last count, there were 77 cases of the Indian variant, which is the latest one that's come out, or we've heard about. In actual fact, it's probably one of the older types that's floating around that has spread rapidly in India. What amazes me is actually that we didn't show more control over who we were letting into the country from India at that time. Anyway, I always believe that human ingenuity will overcome all obstacles thrown in its path, and I'm fairly sure that we will live through these pandemics, we will find a cure, or at least we will use the tools that actually can defeat SARS-CoV-2 infections. And then the worry about is, what is the next pandemic? And I'll leave you with that thought.